Hello, and welcome to this third edition of the Binational seminar, talking about between Manchester University and the National School for Higher Studies, the UNES, in Juriquilla, in Querétaro, Mexico. My name is Alejandro Vargas, and I will be today chairing this session where we are talking about we have two talks today. One is on experimental and computational study of cardiovascular and vascular mechanics by Dr. Jiling Feng, and the other one is parallel and efficient construction of acceleration structures for ray tracing in real time by Dr. Ulysses Olivares Pinto. So let me, I welcome you then to this seminar series, and we will start with the talk by Professor Jiling. I will now give you a short bio of Dr. Feng. So Dr. Jiling Feng is a senior lecturer in mechanical engineering. She was awarded a PhD degree in Brunei University in 2008. Following that, she worked in Loughborough University and the University of Strathclyde as a research associate and research fellow, respectively. In 2012, she joined Manchester Metropolitan as a lecturer and then promoted to a senior lecturer. Dr. Feng has been working in the research area of aging drive model surface engineering and cardiovascular and vascular mechanics. Currently, she is focusing on the experimental study and computational modeling of the cardiovascular and vascular system. She has more than 40 publications in peer-reviewed journals and international conference proceedings, and has successfully won 3 grants from research councils, including the Epsrc, the UKRI, and the GMA-HSN. She has been successful at gaining large joints from funding agencies and has collaborated with international leading academics such as Loughborough University and the University of Birmingham, and leading manufacturing industrial stakeholders. So, Dr. Feng, thank you for being here, and we can now listen to your talk. Remember that you can write your comments or questions at either via YouTube or Facebook Live, and we will have some time after the talk to ask these questions, and hopefully there will be many and will be properly answered by Dr. Feng. Thank you.
Okay, thanks for the introduction from Professor Andrew. Andrew, thank you.
Alejandro,
sorry,
yes.
Andrew. Okay, and good morning to our peers in Mexico, and I think it's good morning. I think
Yes.
Good afternoon to my colleagues in Manchester Met. And now I can share my screen. Okay. Okay, this one I think. Okay, can you see my screen?
No, not yet, but yes, now, okay.
Okay, you see, okay. Just a second. Okay, today's I will give the presentation for this topic, that is experimental and computational cardiovascular and vascular mechanics. As it is introduced by Professor Andrew, I can't forget the name, sorry, and I am Jiling Feng. I am a senior lecturer in mechanical engineering in Metropolitan University. And for today, basically, I will talk about mainly for my current research in the cardiovascular mechanics and vascular mechanics. All this work has been done through the experimental study and also through the computational modeling. And this slide, you can see, is show the outline for this presentation. The topic will be covered, you can see, that include the background information, that is the arterial wave propagation in the cardiovascular system. And I will also talk about the wave intensity analysis. That is the method I am using to analyze arterial waveforms. And I will talk about the applications for this wave intensity analysis. And I will talk about one of my current projects that is currently one PhD student is doing that. That is the detection of the arterial plaque using the arterial waveforms. And also I will give the very brief introduction for my current project, that is a key project from my study. That is a smart peripheral stand for the lower extremity that includes design, manufacturing, and evaluation. This project is supported by the Epsrc grant. That is a collaborated joint project, that is a joint project with Loughborough University and also University of Birmingham. And also I will talk about the another project that is through this CFD modeling to investigate the thermodynamics mechanism for the atherosclerosis formation and development. So firstly, let's look at this arterial wave propagation in the cardiovascular system. That is basically the background information here. So from here, you can see in the middle part, it represents the very brief, schematic for this arterial system. So here, that is ascending aorta that's connected with the heart, and here's arch of the aorta, and here's the descending aorta. Here's the middle part of descending aorta. Here's the abdominal aorta, then split into the iliac artery until the peripheral artery. And when this blood flow is ejected from the heart, that will propagate through this ascending aorta to the descending aorta until the peripheral artery. Then there's a pressure and the velocity blood flow will propagate through the system. So actually we can measure this pressure and velocity. So this graph showed that is simultaneous records of the pressure and the velocity waveform at different sites in the human arterial system. That this figure is from the Pedley's book in 1980. And if we look at this pressure and velocity waveform, actually we can see, for example, this one, you can see that is a pressure. This one is a pressure waveform in the ascending aorta. This is velocity in waveform in the ascending aorta. And here, that is in the further downstream, that is in the right common iliac artery. This one is the pressure, this is a velocity. If we compare these two, you can see actually the pressure waveform and the velocity waveform at a different point actually are quite different. The reason for that is because very complicated structure for these arterial trees. Actually, for the arterial system, actually is a complex, mainly bifurcating tree structure, and that's one branch split into another two branches, and further split into another two branches. So that's very complicated, included lots of bifurcations. So there are approximately 1 million arterials and arterioles. For every bifurcation, the diameter of the daughter vessels actually is gradually less than the diameter for the parent vessel, but combined this area for the daughter vessel is gradually greater than the cross-sectional area for the parent vessel. Similarly, for the length of the daughter vessel, for the length for the daughter vessel is gradually generally less than the length of this parent vessel. And also the geometry and the mechanical property at a different site are quite different. For example, in the aorta is quite distendable, it's more elastic, got more elastic property, and this in the peripheral artery is more stiffer actually. So the with the propagation of the pressure and the velocity waveform that propagated with a certain speed. We call that wave speed. We also call that the Pastel wave velocity, briefed as PWV. This wave speed is a function of the local geometry and the mechanical property. So that's why in the aortic root here is about in the ascending aorta, in the aortic root, the velocity is wave speed is about 5 meters per second, but in the distal artery is increased to 10 to 20 meters per second. Because this arterial waveform, pressure and velocity waveform are related to this arterial wall property, so there are many scientists that are working for over the 100 years working in this area. Then look for this information by using the velocity waveform, pressure waveform, find information that to predict or diagnose for the arterial disease or healthy conditions. So we can use this graph to explain the feature of this pressure and flow or velocity waveform. This one is pressure, this one is velocity. So this graph shows the pressure and velocity waveform at different sites in the arterial system in the dogs. This one is published in the McDonald's book in 1978. So from this one, you can see there are few features we can recognize. One is you can see wavefront becomes steeper. So if we look at here, so from this here, that is ascending aorta pressure in the ascending aorta. This is pressure in the further downstream. And you can see actually wavefront is quite here is quite steeper than this one. And also another feature is the disappear of dicrotic notch. So you can see the disappear of this dicrotic notch, and also the slightly positive wave. This one, the positive wave, has been replaced by the second jump, and also very obviously you can see amplitude increase along this the path of this arterial system. And there are many factors that can contribute this characteristic for this pressure and wave velocity, waveform. One is damping of the wave as they travel. Another one, the effect of reflection, and also has another factor has been suggested is a taper of dimension and the property of the artery, and also for the arterial wall, that is the relationship between the pressure and the diameter, that is nonlinear elastic property. And another reason is the dispersion of the pressure waveform. So there are many factors that has been contributed this characteristic of the pressure and the velocity waveform. So how we can extract the 8 factors factors contribute from each factor on this waveform. So that's why we have this methodology, wave intensity analysis. This method, wave intensity analysis, has been developed by the Professor Kim Parker. Kim Parker is professor in Imperial College. He developed this method in 1990. So by using this method, actually, the waves can be separated into the forward and backward directions. So this one is a fundamental equation for this method of wave intensity analysis that includes the conservation law of mass, conservation law of momentum, and plus the tube law. So we can use this equation to describe the performance of the blood flow in the elastic vessels. And then we use the characteristic solution, characteristic method to get the solution. Then we can split this wave into the forward and backward directions. So here the plus represents the forward direction, minus represents the backward direction. So we can find the forward and the backward pressure, and forward and backward velocity, and forward and backward wave intensity. The wave intensity that is defined as a product of the change of the pressure and the change of the velocity. So here show the example for the separation of the measured pressure into the forward and backward direction. So this is measured pressure. So you can see this is forward pressure, and this one is the backward pressure. And the measured value actually is a superimposition of these forward components and backward components. This vertical line represents the arrival of this backward wave. So this figure is published in the 2007. That is actually from my PhD thesis. And also by using this wave intensity analysis, we also investigated the degree of the wave dissipation. So we have done this experiment and also investigated the degree of the wave dissipation and investigated the different properties. For example, wall property, material, and also for the size of this vessel, and how these factors has an effect on the degree of the wave dissipation. And also we investigated the dissipation for different type of the wave. One is when this piston is pushing forward, another one is when the piston pulling backwards. It will generate a different type of wave, and how this wave will dissipated. And also another one is non-invasive wave intensity analysis. That is also one of my work when I was doing PhD. For this work, that is, I developed the algorithms. Then I further developed this wave intensity analysis. Then this wave can be separated into the forward and backward direction based on the measurement of the diameter and the velocity. So the clinical meaning for this method, the non-invasive wave intensity analysis, that means because we can analysis wave based on the measurement of diameter and velocity. For the diameter, that means we can measure in the clinical setting. When we measure the diameter, we can measure that through the non-invasive way, for example, using the ultrasounds or MRI. And so this method will be further expanded the applications for this method that can be used to analysis for the arterial waveforms. And then this, so you can see here is compared for the result for the wave intensity analysis based on the pressure and the velocity. This one is based on the diameter and the velocity. And for this wave intensity analysis, this method and non-invasive wave intensity analysis currently has been used in many clinical settings. So this one is an example for the aortic pressure and velocity wave in the human ascending wave. So you can see we can separate this measured wave into the forward and backward direction. That is for the aortic pressure and velocity waveform. And also this non-invasive wave intensity analysis has been used for this carotid artery, femoral artery, and also coronary arteries. So that one is basically the background for this arterial wave propagation in the cardiovascular system. And now I will talk about the one of my project currently I'm doing, that's a detection of the vascular, that is a detection of the atherosclerosis, actually using the arterial waveform. So I will talk about the relationship of this atherosclerosis and the arterial waveform. So for the atherosclerosis, actually, that is very important concept related to this cardiovascular disease, because this atherosclerosis is related to many type of cardiovascular disease. So what is atherosclerosis? So atherosclerosis is a type of vascular disease when this plaque is built up along the wall of the artery. The compositions of this atherosclerosis could be the fat, cholesterol, calcium, fibrous tissues, and other substances in the blood. So when this atherosclerosis builds up along the wall, it will reduce the lumen of the artery. And if this atherosclerosis occurred in the coronary artery, it will block the blood flow into the heart, will cause the coronary artery heart disease or heart attack. If this atherosclerosis occurs in the carotid artery, it will block the blood flow to the brain. It will cause a stroke. And if it occurs in the peripheral artery, it will cause a peripheral artery vascular disease. And so the atherosclerosis is the composition and the structure feature is very important to understand the arterial disease, actually. And also atherosclerosis can be classified as a stable plaque, unstable plaque, and calcified and or vulnerable plaques. So for my project, basically, we are doing this intro experimental study, try to link this atherosclerosis and arterial waveform. So this is an experimental setup in my lab, and this is a schematic diagram for this experiment. You can see that include here, this is a Harvard apparatus positive blood pump. It can generate generated the flow waveform that is identical to the clinical, the waveform in the clinical settings, for example, in the carotid artery. And then we can use this measurement setting, that this one is for the flow meter, this one pressure sense for the pressure meter. This one can be measured the wall diameter, wall movement or diameters. Then we put the plug in somewhere at some point inside of the artery. Then we can measure the corresponding pressure, velocity, and also the arterial wall movement. Then we can analyze this data. So this one you can see, we just show this example. So this this blue one, that is for the diameter for the healthy vessel, that means there's no plaque. And the red one, that is for the one type of the plaque, we call that unstable or vulnerable plaque. Here we put that soft plaque, and this black solid one curve that represents the hard plaque. So you can see for different type of plaque, actually corresponding waveform are different. So we can use this method to link this atherosclerosis, different type of the atherosclerosis and arterial waveform. We have some result here and still in the under review for the publication. So here is just one example for the this is a forward waveform, diameter waveform. So we also found actually the components is proportionally related to this backward diameter and backward velocities. And this is another project that is for the that's related computational modeling. That is one of my current projects. That is we using this CFD model, that's the patient specified CFD model, to investigate the hemodynamics mechanism of the atherosclerosis formation and development in the coronary artery. So you can see here we show this picture. We can briefly represent that's anatomy feature for the coronary artery. So you can see here that is the left main coronary artery. Left main coronary artery is connected with the aorta. So here, when the heart is injected in the blood flow, the blood flow will provide the blood into this left coronary artery, provided the blood to heart itself, actually. So here, this left main coronary artery, you can see here, this left main coronary artery can be will split into the two branches here. That is a circumflex coronary artery. This one is left anterior descending coronary artery. Here, that is the angle. So from some previous study, the study think this angle can have the effect of the blood flow performance that could have the effect of this, could be related to atherosclerosis formation and atherosclerosis development. So for this project, basically, we want to look at whether this angle will have the effect for this atherosclerosis formation and development. So from our clinical partners, project partners, we have the CT images, and from CT images, we developed the CFD model, patient-specified CFD model. Here we show these 9 patient-specified CFD model. You can see with the angle, actually, the range of the angle is quite large. Here, this one represents about 45 degrees. This one represents about 120 degrees. Now we do the CFD simulation. We got a result for the pressure distribution, velocity distribution, and also the wall shear stress distribution. So here, that's wall shear stress distribution. However, from this figure, it's not easy to identify this difference between these 9 figures. So we especially observe the particular areas here. One is here, the ridge of the bifurcation, and also the area close to this opposite wall. this wall, and the area close to the inner wall. We identify these three areas, observe the wall shear distribution and pressure distribution, and also for the velocity at these three key areas. We notice actually when the angle increased, the bifurcation angle increased, the wall shear stress at this point actually is exponentially decreased with the bifurcation angle. And also we observe the wall shear stress distribution at this area and this area. We notice the WSS wall shear stress actually in the opposite wall is much lower than in the inner wall. So we can, from the previous study, that is the wall shear stress, lower wall shear stress is related to the atherosclerosis formation. So our study suggested, okay, here that the area is close to the opposite wall is more likely to get the atherosclerosis. This result research finding actually has inconsistent with the clinical research finding. This one we also using the CT image to observe where if the atherosclerosis occur. We notice that actually the 79% of this atherosclerosis also occurring in this area is close to the opposite wall. So that is one of my computational modeling research project. Okay, and another one is that is for this smart periphery stand for the lower extremity, that is design, manufacturing, and evaluation. That is Epsrc funded project. This project, as I mentioned, that is a joint project with within the three academic partners. One is from University of Birmingham, another one is Loughborough University, and also in my group in Manchester Metropolitan University. So in the Birmingham, they basically using the additive manufacturing method to manufacturing the new type of the stand. And Loughborough University is responsible for the mechanical testing, design, and FE modeling. And in my group is basically that is in vitro study for the blood performance related to this stand, and also doing the CFD modeling. And this project had got a lot of industrial support that is from these companies, and also has a clinical support. And currently we got some result. This slide shows some result from this project. So you can see this is a CFD, FSI modeling result for the different type of the plaques. Actually, this is the calcification only model, CFD model, FSI modeling result. This is a lipid only model result. This is the calcification lipid model. So through this this result, actually, we can prepare the CFD or FSI model for the next stage. We will implement the stand into this model for the further investigation effect of this different type of stand, different design of the stand, how this one will relate to the flow performance, how this one will affect the arterial wall movement. Okay, so that is for the brief introduction for my research. And finally, this is a summary for today's seminar. That one is I have done this background information for the wave propagation in the arterial system, and my current project, detection for atherosclerosis using the arterial waveform. And also this one, patient-space modeling for the hemodynamics mechanism for the atherosclerosis formation and development, and the smart peripheral stent for the lower extremity, that is design, manufacture, and evaluation. And currently, I developed this arterial plaque blood system, and also currently has a stent. Okay, this model can be used to investigate hemodynamics performance for the effect of stent in different type of the plaque system. So that is my presentation. Okay, and any questions?
Okay, thank you very much for
your, look at the time.
Very
I don't
interesting
know if
presentation.
it's okay. The time is
let me
okay.
check if we have. Yes.
Okay,
Let me check if there are some questions. People are sending questions. If I don't know if we have some questions. But so far there are no questions. I just have one small question. I was wondering, it's very interesting what you're doing. I was wondering about the in vitro models that you use, the ones, because I see that I really don't know very much about this, but I see that the tubing that you're using to simulate the arteries is submerged in water. Can you say why, and how do you determine how much water, and is that like simulating the body, or you need some pressure on that, or?
Yes, okay, we can go back to here. That is, yeah, this is experimental sighting. Okay, so you can see here's a tank. Yeah, you can see that is water. We can use artificial blood, actually. And also we can control the temperature. So temperature could be 37 degrees, and this could be artificial blood or animal blood, and also is a type of the fluid represent the property of the blood. That's it's no problem for that one. And certainly we also can use the water at moment to represent the blood. And yeah, for the property of this blood, certainly the viscosity of the blood is different from the viscosity of the water. But generally, for the performance, we still can represent the performance for the waveform. Yeah.
It's very, very interesting.
Yeah, thank you.
Investigation and research that you're doing there. Thank you very much. I think we don't have no more questions so far. I don't know.
Okay. Thank you.
Thank you.
Okay. Thank you very much.
So
okay.
We will now...
I can. I don't know the ways. Okay, I need to mute myself. Okay, mute.
Yes, maybe you can stop sharing your presentation so we can now. Okay. So the next, let's move on to the next talk. So the next talk will be given by Dr. Ulysses Olivares, and I will just give a brief summary of what he has been doing. So he's an associate professor at ENES, at the Escuela Nacional de Estudios Superiores in Juriquilla y Querétaro. He has a PhD, a doctorate in computer science from the Center for Research and Advanced Studies of the National Polytechnic Institute from Mexico. He carried out 2 research internships at Intel Corporation in Mexico, where he coordinated the creation of an Internet of Things laboratory. Currently, he belongs to the National System of Researchers. He was a consultant in parallel algorithms for the Food and Agriculture Organization of the United Nations, and has directed multidisciplinary projects through which technological products were obtained patents and copyrights. He's a member of the Association for Computing Machinery and of the IEEE. He has participated as PI collaborator in research projects financed by several agencies here in Mexico and internationally. And his research lines focus on high-performance computing, computer graphics, and computational biology, and that is what he will be talking about today. So, Ulysses, maybe you can start sharing your screen and tell us more about this.
Well, thank you very much, Alejandro, for your introduction. I'm going to share my screen. Now you're seeing it, right?
Yes.
Okay, perfect. So thank you for the introduction, and thank you to the organizers for organizing this meeting. And I hope this is going to be one of the many more encounters between the two institutions. Today, I'm going to present a specific topic that is related with computer graphics. So my talk is going to be entitled Parallel and Efficient Construction of Acceleration Structures for Ray Tracing in Real Time. So we're using an algorithm that is called ray tracing. So ray tracing is a quite interesting algorithm that can produce really realistic animations as the one that we're seeing right now in the screen. And we can use this algorithm in order to produce those images or in order to produce some animations. So in order to establish a context, I would like to start by defining what rendering is. So rendering, it's a process of converting three-dimensional models into two-dimensional images. And of course, for doing that, we're using a computer. So everything starts as an idea. So the first step is to have that concept or that idea, and then to materialize that concept in the way of a three-dimensional model. Once we have that model, we can assign some textures in order to add some realism to that model. And in addition to that, we can add some animations too. We can achieve that by implementing some linear transformations or more complex transformations too. In addition to that, we can add some lighting, and then we can make some camera adjustments. And in the final process of obtaining this, process of the two-dimensional image, it's called rendering. And basically, we put together all the previous steps, and then we produced a render or an image that it's the projection of that three-dimensional world, and we can display it in a two-dimensional image. So there are many ways to rendering, models. There are two techniques that are the most known. The first one is rasterization on the left and ray tracing. With rasterization, we only can project that three-dimensional model or three-dimensional world into a two-dimensional image. And ray tracing works in the same way, but we can obtain more effects, such as reflections, as the one that we're seeing right here. And those reflections are naturally produced by this algorithm. In addition to that, we can also produce some shadows, as the one that we're seeing here. And actually, this algorithm is quite interesting because with those effects, we can produce some realistic images. So in order to explain this algorithm, I'm going to use different components. So this ray tracing algorithm, it's as I already said, it's a rendering technique that simulates the interaction between light and objects in a three-dimensional scene. So let me use this pointer. So we have different components here. We have a camera, which is going to be denoted as the origin position. This is going to be the equation for tracing an array. Then we have different components here. We have a camera, and then we have a virtual image, which will contain a lot of pixels. So those pixels are going to be defined by the final user. So we have geometry too, which in this case is a simple sphere, and we have some light sources. So from this origin, we're going to trace an array for each pixel of this scene, and then we can continue the path of that ray using a direction. And then direction is given just for this position on this virtual image. And if we continue that path, we're going to have our first intersection. From this first intersection test, we're calling this primary ray, and then we're going to trace another ray that is called shadow ray. Those shadow rays actually are quite useful in order to calculate these shadows. If we have an object that it's between the light source and then the original object, we can produce some shadow over here. If we produce this process in an iterative way, we're going to produce this projection of this three-dimensional model into a two-dimensional image. And with this algorithm, we can produce a lot of images with high quality, as the one that we're seeing right now in our screen. We can achieve global illumination effects, and it could be achieved in a simple period of time. So we can achieve high quality models as the effects that we're seeing right here, reflections and refractions of the light. And to better explain how this algorithm works, I'm going to use a simple video where we have this primary ray, and this ray is going to bounce in the scene. And in each bounce, this ray will contain the information related with color in this image. So the final bounce is going to bounce to the light source. So let's imagine we're going to render a 4K resolution image, which nearly we will have 8 million pixels. So let's imagine too, we are going to have a really complex model that we are going to be composed by 12 million polygons. So in order to produce a single image using this algorithm, we need to perform 100 billion operations. So if we want to achieve, an interactive frame rate, which means we need to have at least 24 frames per second. So we need to produce 24 of these images within a second. So that's really complex to achieve. So there are many applications for this algorithm. One of them is CAD applications we can use for design and stuff like that. We can use this algorithm also for visual effects, for scientific visualization, scientific simulations, optics. In this respect, it's quite interesting because we can assign properties, we can assign materials to objects in a scene. So we can simulate how those objects will be behaving when we trace this algorithm. Maybe you are actually familiar with this one, animated movies. We can use ray tracing in order to produce these high quality animated movies. Also in architectures and in the aerospace industry, actually it's quite useful to find this. So we have defined different components of this algorithm. One of them is geometry. So how geometry is formed using this algorithm and in general, whatever algorithm in computer graphics. So the main a computational model that we are going to use are polygonal meshes. Those polygonal meshes are formed using a set of vertices, and those vertices are interconnected using edges, and that interconnection forms three-dimensional models. So once we have that three-dimensional model, we can assign some textures, as I already said, and we can add some realism to this object. So one of the main problems with this ray tracing algorithm is that we need to find the exact point in which a ray will intersect with that object. So that's a really complex project. That's a really complex thing to achieve because we have to perform too many queries to this geometry. So we have to find not only all the intersection tests or all the intersection points, but we have to find the closest intersection point. So that would be really hard to achieve. And we're going to have a linear complexity, a complexity of big O of n, and we can decrease that complexity if we store that information, if we store that, in this case, that geometry in a structure, in a type of structure that we can sort it and we can, make those queries in a faster way. So we can doing that by storing that geometry in some acceleration structures, which actually are called like that because they are accelerating the ray tracing algorithm. And in that way, we can decrease the computational complexity from a linear complexity to a sublinear complexity, which is actually really good when we want to try to achieve a lot of operations within a second. So this is one of the most implemented methods in the state of the art for accelerating ray tracing. So we're going to use actually this technique in order to produce more realistic images, but also produce those realistic images in real time. So that would be our main focus in this presentation. So there are different types of acceleration structures. We can have uniform grids, which actually subdivides the space uniformly. So they're quite simple. So they take the space and they subdivide that space in a uniform way. In addition, we can have K trees where we're going to have a binary tree and we're going to partition the space, not the geometry, only the space. And we can have a third class of acceleration structure, which are called bonding volume hierarchies. Those structures subdivide geometry, not space, only geometry. So that would be interesting because it depends on the input geometry. We will have different performance for these acceleration structures. So we proposed a work some years ago where we automatically select what would be the best suited acceleration structure given an input geometry. So we extracted some characteristics from that geometry, and then we, once we characterize that geometry, we select a specific acceleration structure that it's going to be the best suited for that geometry. So if you have time, you can check that paper and you can see all the details about that work. So our contributions for this talk are going to be focused on polygonal geometry. So we have been working on different works within computer graphics, and the one that I'm going to present here, it's focused on polygonal geometry. We're also working with another type of geometry, which is called non-uniform rational B-splines, which actually are a specific type of geometry here in computer graphics and in general in ray tracing. So with this type of geometry, we're producing mathematical functions instead of representing geometry as polygons or triangles, for example. So continuing with this talk, we summarize these contributions into aspects. We proposed a binary partitioning approach, which is based on the binary representation of the input, the number of the input geometry, with the number of polygons that will form an object. And then we proposed an efficient construction using parallel programming, using the advanced vectorial instructions that are available on the current GPU architectures, but also we use GPU architectures in order to parallelize those operations. And we can achieve in that sense real-time frame rates, which is the main objective of this work. So I'm going to summarize the contributions of this work using this pipeline for ray tracing. So in this common pipeline for ray tracing, we have 5 steps. In the first step, we're going to launch that application, that ray tracer. Then we're going to build the acceleration structures. Then we're going to generate all the rays, and then we're going to perform all the intersection tests. And finally, we're going to produce this frame buffer, or the final 2-dimensional image that it will contain all the projection for that 3-dimensional world. So our contributions are given in this red rectangle. So the first thing that we did was to build an acceleration structure based on how many children will have each node. So if we have, for example, an architecture that supports AVX, advanced vectorial instructions, of 128 bits, we're going to use only a BBH4. If we have an advanced vectorial instructions which supports 256 bits, we're using a BBH8, which means we are going to have a branching factor of 4 or a branching factor of 8. Then we're using an a priori construction. In this a priori construction, we're going to define how many primitives each node will contain, and then we're going to perform all the parallel operations in CPU and GPU architectures, and then we're finally assigning those primitives, those polygons, to nodes. And once we have that, we can perform all the intersection tests, and we can generate all the rays, and finally we can produce that intersection, that final frame buffer, and hopefully we can have these operations in real time. So we're going to see some results in short. So the first thing that we do here is we proposed a hybrid construction. So one of the most implemented methods for building acceleration structures is bind SAH, which is a metric quite interesting. It's based on an optimization algorithm that selects the best way to partition an input geometry. So we're using this type of partition only for the first level, and then for the rest of the levels, we're using our binary partitioning approach, which is actually a really quick partitioning approach because we are, checking some two basic rules that I am going to define in short. So we can have different branching factors. We can have 4 nodes or 8 nodes, and it would depend on the architecture, or implementation automatically selects the most suited implementation or acceleration structure given the input geometry, but also the architecture in which we're running that implementation. So if you want to see more details about this research, you can see those 2 papers, and then you can see all the details on how we build this construction. So in order to define, or in order to partition that geometry, we need to assign a specific number of primitives per node. So we're going to start from the binary representation of the number of primitives or the number of polygons that we're going to have in a specific node. And then we're going to define the cardinality of n as a number of primitives. And of that number of primitives, in this case, let's assume we have 13 primitives. So we're going to use the binary representation for that 13 number. And in this case, we're going to extract, well, we're going to have this binary representation in a left-right order. So we're going to extract all the radix digits, and those radix digits will indicate us how many polygons we're going to assign for the left node, and how many primitives we're going to assign to the left node. So here we have this formula, which is actually quite simple, and this k is given for the radix digit of the most representative bit in this case. In this case, we have a radix digit of 3, and then we can obtain this number, which is 2 to the k, which is equal to 2 to the 3, which is equal to 8. And then we can calculate this r using, well, we can clear this r from this original formula, and then we can assign this 13 minus 8 is equal to 5. So using this formula, we can assign how many primitives will contain each node. So based on that, we're going to define two partition rules. If our binary representation starts by 1, 0, we're going to assign 2 to the k minus y plus r primitives for the left node, and then we're going to assign 2 to the k minus 1 for the right node. On the other hand, if we're going to see if our binary representation starts by 1, 1, which is the case of 13, we're going to assign 2 to the k for the left and r for the right. So once we define those rules, we can build our binary tree, or in this case, on an oct tree or a quad tree. It depends on the number or the branching factor that we will have. But one of the most interesting parts here is that once we define this a priori construction, we're going to define how many primitives each node will contain. If we have that, we're going to build, or we're going to guarantee that we're going to build a complete tree. A complete tree means that all the levels are complete, with the exception, or with the possible exception of the last level, in which we can have some incomplete trees. But the problem when we have incomplete or invalid nodes is it's that we cannot continue iterating over this structure, and we have to perform a backtracking, and that has a high penalty in time. So we don't have to have that. And what we do is to produce this tree that it will be complete. So that's a really positive thing. So once we define how many primitives which each node will contain, so we need to assign that geometry to that nodes. So in order to perform that, we are summarized in 3 steps. First, we're going to find the longest axis, and we perform that using a parallel reduction, finding the minimum and maximum values, using a GPU architecture in order to analyze those input values in a parallel way. And then we're going to group those primitives or those polygons in coherent clusters. So once we have this grouping, we can assign directly to those primitives to nodes, and then we can finish our construction. So I'm going to describe how we can assign those primitives to coherent clusters. So for doing that, we're using a representation that it's called Morton codes. Morton codes are quite interesting because they can compress the representation from a two-dimensional representation into a single-dimensional representation. And it would be the same for three-dimensional data or for n-dimensional data. So it would be interesting because we can have a single integer value that is going to compress all the other dimensions. So with that single value, if we order that single element, this element will have, or will follow this C order, which would be actually interesting because we can clusterize data using this order, and we can make our first clusters. So once we define those clusters, we are going to match those input Morton codes using a hash function, and we can make it in constant time, and then we can map those input Morton codes to specific clusters. And as a result, we're going to have our geometry partitioned in coherent clusters, and that would be actually quite interesting because when we're working with this type of a coherent geometry, we can assign in practice, we are producing a lot of arrays. So we're tracing packages of arrays, and if we have those queries using the coherent primitives, we're going to have a better performance. So once we group that geometry and that primitives in coherent clusters, we can assign directly to nodes, and then we can maximize the probabilities of an intersection for arrays that are coherent between them two. So in order to validate this model and this, this implementation for this algorithm, we used different scenes. We're using really simple scenes from 700 primitives, and all the way the complexity is increasing through all the scenes, and then we can achieve, or we can use the Asian Dragon, which we will have 7.4 million primitives. So this is a really simple model, and this is going to be a really complex model. So we use different scenes in order to produce this, or in order to measure the performance of this algorithm. And here are some results that we found. So this is our implementation is denoted by the blue color. In all the cases, we're analyzing three metrics: construction times, frame rate, and the number of intersections per box and per primitive. Those are the three main metrics that are, if you want to analyze how efficient this an algorithm or an algorithm is, you need to evaluate those two metrics. So what we're doing here is that we're obtaining lower construction times, which is actually really good. If we have lower construction times, it's good because we have to rebuild an acceleration structure every time. In the case that we're using dynamic scenes. In the case of static scenes, we're not using, we're not rebuilding this acceleration structure on every frame. We rebuilt it, or we built it once, and we can traverse all that acceleration structure multiple times. But in dynamic scenes, it's quite important to have lower construction times. So in all the cases, we are having lower construction times by a factor of 300. So yeah, the frame rate, it's quite interesting here because the models that we're analyzing right now are static scenes. So that since we are having, less in this case, a frame rate, but it was expected because we're using a simple partitioning approach, which is quick, but it not has the same performance as SAH, being SAH, which is the most efficient, in this case, the most efficient method to build acceleration structure. So what we achieved was a balance between quality and time. So that was actually quite good. So the final metric that we analyzed was the intersection per box and per primitive. So when we're going to perform different intersection tests, we're going to analyze how many intersections per box and how many intersections per primitives. When we're referring to these intersections per box, we're assuming that we're going intersecting these nodes, these nodes. And when we're analyzing the intersections per primitives, we're going to analyze intersections per leaf nodes, which are individual geometry or individual triangles. So the good thing, or the thing that we want to see here, is to have a lot of intersections per box, but fewer intersections per primitive. So what we see here is that our method followed that pattern. In the case of the method of the BIMP SAH, we have fewer intersections per box and a lot of intersections per primitive. So the red color, I didn't say that, but the red color denotes how many intersections in this case per box perform that method, and the green color how many intersections per primitive. So we can see the same data here in this graph, but it's better to see in that image. So as a conclusion, I would say that this this implementation it was quite efficient, and it we found a balance between construction times and then performance of that algorithm. So we presented a binary partitioning approach for building a complete hybrid bounding volume hierarchy. And then we used a linear clustering algorithm for grouping polygons in coherent clusters. And we performed that in linear time. So in order to decrease that computational complexity, we extensively used some SMID extensions, which are parallel programming, in fact. And we implemented that, taking advantage of that parallel CPU and GPU architectures. And finally, this method could process in a processor and nodes using this approach. And finally, we're going to say that this construction approach outperformed the most efficient partitioning approach, which is in this case, it's been SAH by a factor of 300 in construction times, and it attained the ray traversal performance for most of the scenes. So the thing here is that we are going to have less 99% for static scenes, but in the case for dynamic scenes, which I didn't present the results here because I didn't have enough time, we're having plus 15% performance on dynamic scenes. As I already said, when we have dynamic scenes, we have to update or we have to rebuild from scratch that acceleration structure on every frame. So it's quite important to have faster construction times for that. So just to finish my presentation, I would like to acknowledge these projects. I would like to thank CONACYT, Ciencia de Frontera, UNAM de Gapapapit, and UNAM de Gapapapime for funding this research. Thank you very much. If you have any questions, I'd be glad to answer them.
Thank you, Ulises. It was a very nice presentation. I also enjoyed it a lot. I think we have very little time for questions. Let me check if there are some questions. Apparently, we don't have any questions right now, but we're already over time. So I just wanted to ask one simple question, but you answered it already. That was the difference between a dynamic and a static image, because I think that with a dynamic image, you need to do this as quickly as possible, if I understand correctly.
Yes, that's correct. With dynamic scenes, we have to rebuild that acceleration structure from scratch, from the beginning. And in the static scenes, we only built it once, and that's it. We don't have to build it each time. So that's the main difference. In dynamic scenes, we have movement, and static scenes, those are rigid objects.
Okay. Well, I think that's about it. So I thank you again for your participation, and remember that this video will remain in the YouTube channel, I think. So if you want to keep asking questions, we will make them available to the speakers, and maybe they can then answer directly there. So thank you. It was a very nice seminar today. Goodbye.
Thank you. Take care.